Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at the averages of random variables. This is actually going to be the first part of a two-part series. Today we're going to look at basic concepts and the properties of expectations. Turns out that there are several different interesting ways that we might average a random variable. The most common and one you might be familiar with is the mean. So let's look at that first. The mean. The mean value. All right, let me give you some notation first. A lot of times the mean value will be designated like this, a lowercase mu, Greek letter. It's also represented this way with a capital E. This all means mean value. Mean value of some random variable, capital X. All right. This designation means expectation. Expectation or expected value. When someone talks about the expected value of a random variable or says they are taking the expectation, what they're meaning is that they're finding the mean value. So capital E stands for expectation or expected value. We'll use that somewhat interchangeably. Sometimes we might even, in some cases, depending upon the random variable, my mean value might be designated by a little m. We've seen that when we've talked about the Gaussian probability density function in the past. Most commonly, I'll use either the lowercase mu or I will use expected value. Probably the lowercase m will, in most cases, be reserved for the Gaussian probability density function. All right, so how do we calculate the expected value? Let's begin this way. For a discrete random variable, the expected value is calculated this way. It's calculated as a weighted sum. All right, this is what's called a weighted sum average. A weighted sum average. The expected value of a random variable, in this case we're assuming that x is discrete. All right, and what we do is we add up the product of each value, little x sub I, times the probability that my random variable takes on value little x sub I. So let's take a look at a limited special case. Special case. Let's assume that all values of my random variable x, little x sub I, let's assume that all little x sub i's are equally likely. That's a limited special case, but it'll yield an interesting result. If that's the case, then the probability that x equals x sub I, that equals 1 over n. And of course we're assuming here that there are n values of my discrete random variable x. All right, and so if each value of my discrete random variable x is equally likely, then the probability is simply 1 over n. Well then, in that case, the expected value is summation I equals 1 to n x sub I times the probability that x equals x sub I. And that's just going to be 1 over n times the summation I equals 1 to n of x sub I. All right? This is, let me summarize it here, for a discrete random variable where all of the possible values of my random variable are equally likely. This is the way I would find the mean value. This is a limited special case. What I do is I add up all of the values, and divide by the total number of values. This is exactly the same way that you would calculate what you might commonly have referred to as the average test score. So if I give a test in this class and there are 30 students in the room, I add up the scores for each of the 30 students and then I divide by 30. That's the way we would find the average score. Really what we're finding is the discrete mean. All right? So this has been used. You will probably have seen this the way we commonly find, and I'll put this in quotes, average test scores. Really what you found is the mean of a discrete random variable, the random variable meaning the scores of the students on a particular test. All right, so this should look familiar to you. All right. Let's go back one slide and look at this result a bit more generally. This is the weighted sum average. All right. This is also known as the relative frequency approach. My probability here is actually a relative frequency. All right, so let's look at that a little bit. Let's do an example for that. Let me write down my result up here. I've got the expected value of x. This is for my discrete random variable. Okay, I claim that that's the way we're going to find the mean value of my random variable. Let's look at this table. I've got 100 students who are taking a class and they take a test. So my random variable is test scores. All right. I've got a table over here of relative frequencies. All right. So for example, the relative frequency for students who made a 90% on the test is 10%. And the way I get that is 10 students out of the 100 divided by 100 students who took the test equals a relative frequency of 0.1. All right? So what that's saying is the probability of making a 90 on the test, the probability that my random variable equals 90% is 0.1. Those probabilities up here, the probability that my random variable takes on a specific value, in this particular case, is a relative frequency value. All right? All right, so let's use our relationship in the upper right-hand corner of the page here to find the average or the mean value of test scores for this class of students. So the mean value is just going to be a value of 100, that's x sub I in this case, times its relative frequency, 0.02. 2%. 2 students out of 100 made 100%. Plus 95 times 5%. Plus, I'll let you write all this down. We've got 60 times, 3% looks like. Plus, 55 times a relative frequency of 0.01. And if you work all that out, you get to be a value of 80. All right, so the mean score is 80. What does that mean? What does that mean? The mean score, and oh, by the way, if you had gone in and done this in the rather traditional way, if you had added 100 2 times, and add 95 5 times, and 90 10 times, 85 20 times, etc., 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 all the way down, and then divide by 100, you would get the exact same value of 80. All right, try that for yourself. The relationship in the upper right-hand corner, which uses the relative frequency approach, which is a weighted sum, yields the exact same value that you would have gotten if you'd have done it the old-fashioned traditional way. So what does mean value mean? What does that mean? The mean value little mu sub x, is the point above which and below which my random variable is 50% likely to lie. In other words, the probability that my random variable is greater than or equal to the mean equals the probability that my random variable is less than mean. And I do tend to draw my mu's backwards. I apologize for that. It's an old bad habit. That's hard to break. That's supposed to be the mean. This equals exactly a half. All right? So it's 50% likely that my random variable will be above the mean or below the mean. So let's draw a simple Gaussian random variable. Right here, we've seen this is the mean. Let's draw my mu the proper way. It's 50% likely that my random variable will lie above the mean value. And it's also 50% likely that my random variable will take on a value less than the mean. Okay, that's what that means. Mean is the 50% point. It's 50% likely to be above the mean, 50% likely to be below the mean. All right. Let's generalize the calculation of a mean value a little bit. So, for a discrete random variable, the expected value of my random variable is this. This is discrete. That's a discrete random variable. For a discrete random variable, I find the mean by using a relative frequency approach or a weighted sum. All right? Both of those characterizations are correct. What about for a continuous random variable? For a continuous random variable, we do this. I replace my summation with an integral, and I'm going to integrate over all possible values. Let's make that look a little bit more like an infinity on the top. And instead of having specific values, little x sub I, I'm going to multiply. I'm going to put in a variable x, and instead of having discrete probabilities, I'm going to have a probability density function All right, so my summation becomes an interval, my discrete values become a variable, my discrete probabilities become a probability density function, and I average. All right, this is for, actually this is actually true for both discrete and continuous random variables. It's true for discrete random variables if I express the probability density function here using a collection of delta functions. So this is most commonly used for continuous random variables. And discrete random variables if the PDF is expressed as a summation of weighted delta functions. When we first introduced the notion of probability density functions, and we looked at the probability density function for the random variable equal to the sum of spots up when I tossed 2 fair dice, we ended up with a PDF that was a summation of delta functions with a bunch of weighting values in front of it. In any event, this is the most general way for calculating the mean value of a random variable. Okay. Let me now introduce another average of a random variable in a very general way. I'm going to introduce the concept of standard deviation. We'll come back and we'll calculate this with more precision in just a few minutes. Let me just introduce the concept a bit generally now. So standard deviation is commonly designated with the symbol sigma. That's a lowercase Greek letter sigma. And the standard deviation is really intended to be the mean spread of values about the mean value. It's the mean spread of values about the mean value. Mean spread of values about the mean value. So you've seen me draw this before. This is a Gaussian distribution. Here is the mean value. It's 50% likely that the random variable will be above or below my mean value. And you've seen me draw something like that and say that sigma is a measure of the width of my probability density function. All right? And that's true. In fact, sigma represents the mean spread of values about the mean value. All right. How do we calculate that? I'm just going to do this in a bit of a hand-waving heuristic way for the time being to introduce the general concept. We'll come back and calculate it with a bit more precision a bit later. So how do we calculate it? I want to build this up. Sigma equals. The first thing we're going to do is we're going to take our random variable, x, and I'm going to subtract the mean. All right? Take my random variable, and I'm going to subtract the mean. This is a new random variable. Remember, a function of a random variable is also a random variable. X minus its mean is now a 0 mean. Random variable. X itself is not necessarily a 0 mean random variable, but x minus its mean, x minus mu x, is a new 0 mean random variable. That doesn't look much like an R, does it? 0 mean random variable. Okay, well, x minus its mean might yield values that are negative. So the next thing we're going to do is we're going to square that. All right? I'm going to square that to make everything positive. I'm going to square that to make everything positive. And then I'm going to find the expected value of all of this. All right? I'm going to take my random variable, x, subtract its mean. Specific values of x minus the mean could be positive or negative. Really what I'm interested in is the distance and not the sign. So I'm going to square everything to make it positive. I'm going to find the expected value of that. And then I kind of want to undo the initial squaring. And so I'm going to take the square root of all of that. All right? So my square root here is to undo the initial squaring. I'm going to undo taking everything to the second power, more or less. More or less. I know that's not exactly the way it's done, but this is commonly the way it's done. All right? Let me make an aside note over here. Note. The expected value of any random variable minus its mean is exactly 0. So if I had not, so let's think about that for a second. If I take any random variable and subtract its mean, this is a new random variable, y, and this is a 0 mean. That's a 0 mean random variable. In effect, what I do is I take the mean and shove it back down to 0. The expected value, or the mean value, of a 0 mean random variable is exactly 0. If the mean of a random variable is 0, it's 50% likely to be above 0 and 50% likely to be below 0. The expected value of a 0 mean random variable is 0. If I had not squared x minus mu x at that step, the expected value would be exactly 0, and that would not be very helpful. So this is the reason we take x, subtract mu x, square it to make everything positive, find the expected value of that, and then more or less undo the initial squaring by taking the square root. All right? One more thing before I move on is if we square sigma, we get this. And in the past, you've heard me use this. Sigma squared is variance. We'll come back to that a little bit later on. The expected value of x minus mu x squared is known as the variance. The variance is the square of the standard deviation. All right. Hang on to that for a minute. We'll come back and talk about variance and standard deviation a bit more in a few minutes. First, though, let's talk about how to find the mean value of a function of a random variable. Let's find the mean value of a function of a random variable. In other words, I've got a random variable. Let's try that a bit better. My initial random variable is x, and a new random variable is y is some function of x. Okay? All right. Well, previously, we've seen this. This is the way we found the probability density function for y based on knowledge of the probability density function for x and the transformation function. The way I've written this here, go back and check your notes, I'm assuming that g, in this case, notice I don't have absolute values here. We'll assume that g of x is always monotonically increasing or always non-decreasing. Always non-decreasing. This is another way of saying that it's monotonically increasing. All right. The result that I'm going to come to in just a minute is going to be entirely general, but it's easiest for me if I do the following analysis, assuming that my transformation function g is always non-decreasing. That allows me to throw away the absolute values around the derivative of x with respect to y. So the expected value of y is then that's my continuous way of calculating the mean value of y. This is also the expected value of g of x, because g of x equals y. All right, and this equals y equals g of x. My probability density function for y is then alright, so let's look what I've done. Y equals g of x. My probability density function for y equals that relationship that I get from up here. And I have to preserve my dy here. But then these dy's cancel out. All right? So what I end up with is the expected value of a function of x equals the integral from minus infinity to infinity g of x times f sub x of x dx. Right? That's my general result. We'll write that down again in just a second. Let's go do that a little bit better on the next page. So, in general, the expected value of a function of a random variable equals the integral from minus infinity to infinity g of x times the probability density function of x dx. It turns out when I started this derivation I said that my transformation function g was always non-decreasing. It turns out if I looked at always non-increasing functions and did some mathematical gymnastics, I would come to this exact same result. This is true for all g. Okay, that's true in general for g always increasing or g always decreasing, or anything in between. All right, what happens if x rather is a discrete random variable? Let's reduce this a bit. So this is my general result. Beg your pardon. But let's look at a special case if x is discrete. If x is discrete, then my probability density function is a delta distributed function. It's going to be summation from I equals 1 to n, the probability that x equals x sub I times a delta function x minus x sub I. All right, I refer you back to look back at the PDF for, but for my random variable x equals the sum of spots up when we toss two fair die. Sum of spots up when we toss two fair die. Okay, go back and look at that example where we calculated that the probability density function was a collection of weighted delta functions. All right. So if we plug my probability density function for my discrete random variable back up into my general relationship at the top of the page, we get this. Plug that back into the relationship at the top of the page. All right. That reduces to oops. Okay. All right, so what we have here are two relationships that we can use. This relationship at the bottom of the page we can use if x is discrete. Really, that's a simplification of the relationship at the top of the page, which is actually the most general result. This is true. This relationship is true in general for x discrete or continuous. Relationship down here at the bottom of the page will help you. It's a simplifying step, I suppose, in the case when x is discrete. Okay. Let's talk about some interesting functions of random variables. Let's talk about moments first. Moments. All right. My function g is going to be my random variable raised to some power m. M is an integer here. M is not intended to be a mean value. It's just an integer. All right. In this case here, m is just an integer. All right. The expected value then, the mth moment, is the expectation of x raised to the mth power, and that is integral from minus infinity to plus infinity of little x raised to the mth power times the probability density function of x integrated over all x. We have a couple of special cases. In fact, really the only two that we're going to look at is if m equals 1, we have the mean. The first moment is the mean. First moment is the mean. If m equals 2, we have what's called the mean squared value. This is the second moment. For our class, we're not going to look at third, fourth, fifth, sixth moments. We're not going to look at moments higher than the second moment. For reasons that I will describe in just a few minutes, I'm going to do an example first. The mean squared value is also known as the square of the RMS value, and also known as the normalized power. And I'll get to what I mean by normalized power in a minute. All right, we'll talk about what I mean by the mean squared value being the RMS squared value, and also what I mean by the second moment being the normalized power. Let's do an example first, though. Let's assume that I've got a uniform random variable. I've got a uniform random variable. It's going to look something like this. My probability density function, rather, is going to look something like this. All right. And this is the peak value is going to be 1 over b minus a. Area, of course, is going to be 1, as is the case of all probability density functions. So unit UNIT area. Okay? Just by looking at this probability density function, you can probably guess that my mean value is right there in the middle, and that it equals b plus a over 2. Right in the middle. No surprises there. But let's calculate it. All right. My expected value my first moment is integral from minus infinity to infinity of x times the probability density function of x. In this case, it's going to be an integral from a to b of x times 1 over b minus a. And this equals x squared over 2b minus a, which equals b squared minus a squared over 2b minus a. And after doing some factoring, you can do the factoring. I'll just write down the steps. It'll be b plus a times b minus a over 2 times b minus a, and that is b plus a divided by 2. So we get the result we expect. All right, you check my math. Make sure I do the factoring correctly. What about the second moment? First moment, for the uniform probability density function, we can pretty much just write down. It's pretty obvious. But I wanted to do the math to show you that this calculation up here actually gives us the result that we expect there. All right, what about the second moment? This is not quite as obvious, but let's go ahead and do it. The second moment is going to be the integral from a to b, x squared 1 over b minus a dx. This equals x cubed over 3 b minus a, evaluated from a to b. That equals b cubed minus a cubed over 3 times b minus a. And I'll let you do the factoring steps. After some factoring, we end up with a squared plus ab plus b squared over 3. And I'll admit, that's not really so obvious to me. That's the mean squared value. All right. And I notice that I left something out up here. When I did my integration, I need to integrate over limits a to b. Apologize for that. All right. So just hang on to that. This is the mean value and the mean squared value of a uniform probability density function. We'll use that a little bit later on. Let's talk now about the mean squared value as normalized power. All right, so let's think about something hopefully you've seen before. Recall a simple circuit. And I've got some voltage V, and I'm going to drop that voltage across some resistor R, and that's going to give me some current I. All right. What is the average power dissipated by my resistor R? P average. That's the real power, sometimes also known as the real power. That's the power that if you touched that resistor, it would burn your finger. All right. That's the real power. It's the real power that's being dissipated by that resistor. That is the RMS voltage squared divided by resistance. All right, hopefully you've seen that before. The average power dissipated by a resistor is the RMS value of my time-varying voltage signal, V of t, square of the RMS value divided by the resistance, V squared over R. Well, how do I find RMS value? Remember, it works backwards. RMS means root mean squared. RMS means root mean squared. First thing, and I work backwards. First thing I do is I square my voltage. I square my voltage. Then the next thing I do, first thing I do, when I find RMS, I work backwards. I square it first. Then I'm going to find the mean value. For a time-varying function, it looks like this. Integral from minus t over 2 to t over 2. I integrate, and I divide by my window of observation, capital T. And then I find the square root. I undo all of that. I undo all of that. The last thing I do is take the square root. That's what that means. The RMS value of V as a time-varying function is its DC equivalent. That's the DC equivalent voltage. Hopefully you recall that from some circuit analysis example or course. All right? Then to find the power, I divide by resistance. All right? If R is 1 ohm, we have what's called the normalized power. If R is 1 ohm load, my average power is what we call the normalized power, sometimes just designated P sub n, the normalized power. All right? So look what we have here. We have the normalized power is just the RMS value squared. All right? Let's look at the second moment. The second moment what am I doing? The first thing I do is I square my random variable. The second thing I do is I find its mean. The square of the RMS value is just the mean squared. Does that make sense? If I square the root mean squared, I just get the mean squared value. RMS squared, let's go back over here, RMS squared equals mean squared. All right? RMS squared is mean squared. Likewise, the second moment is the mean of a random variable squared. And you'll notice that down here, I'm not dividing by resistance in the same way that right here, I'm not dividing by resistance. Sometimes my random variable x is maybe a voltage signal or maybe a current signal. It could be a random voltage that's driving, it's maybe a noise voltage that's resulting in power delivered to some load resistance R. So for this reason, my second moment is sometimes known as the RMS value squared, and it's also, looking back up here to the top of the page, my mean squared value is sometimes known as the RMS squared value, and by analogy to my circuit example, it's sometimes known as the normalized power. If my random variable x represents a noise voltage or a noise current, that would be, the mean squared value would be the power delivered to a 1 ohm load resistance. All right? All right. Let's talk about another function of random variables. Central moments. All right? Central moments are going to be found by finding the expectation of a random variable after subtracting its mean. All right? Look something like this. I'm going to find the expectation of a random variable after first subtracting off the mean and raising to some integer power n. All right? So in this case, n, this is the nth, excuse me, this would be the nth central moment. And n here is an integer. All right? And you'll notice that when I subtract the mean from any random variable, I get a new random variable that is 0 mean. X itself is not 0 mean, but x minus its mean is a new 0 mean random variable. Okay? this is calculated, the nth central moment is calculated this way. Integral from minus infinity to infinity, x minus mu x to the nth power. That's not very clear. Let me redo that. I dropped my eraser. Times the probability density function. Okay. My function now, if you will, is x minus mu of x raised to the nth power. So I plug that into my integrand, multiply it times the probability density function for x, and integrate over all possible values. Okay? And of course, mu of x is my first moment, or just simply the mean of x. All right. Let's look at a couple of special cases. If n equals 1, this is my first central moment. That's my first central moment. M sub 1 is the expectation of x minus mu of x. And as we've discussed before, the mean value of a zero mean random variable is exactly 0. If I take x and subtract its mean, I get a new random variable whose mean is 0. The expected value or mean value of a zero mean random variable is exactly 0. What about n equals 2? My second central moment is what? The expected value of x minus mu x squared. What is that? Hopefully you recall from a few pages back, this is my variance, which is the square of the standard deviation. My second central moment is the variance. My second central moment is the variance. All right. All right. Turns out that there's fairly handy ways of calculating variance without using the relationship in the upper right-hand corner. Turns out that if I know the mean and the mean squared value of a random variable, I can find the variance very quickly. Let's look at that. We'll do that by examining the properties of expectation. Properties of expectation. There are three properties. First property is that the expected value of a constant is a constant. The expected value of any constant, the mean value of any constant is that constant. The mean value of 6 is 6. All right? Second property. The expected value of a constant times a function is just a constant times the expected value of that function. And the third property is the expected value of a sum of functions is just the sum of the means. Okay, those are the three properties. Let's do an example. We're going to do three examples. We'll do three examples. So, first example. What if my function is my function's that? All right. I want to find the expected value of g. And we know this to be my variance, the square of the standard deviation. All right. Let's multiply what's inside of my expectation here. This is going to be x squared minus 2x times mu x plus mu x squared. And this is going to be that's that. Applying my properties. And so this is just going to be expected value of x squared, or my mean squared value, or my normalized power, minus 2. That's not a very good mu. That. Expected value of mu x squared is just mu x squared. The expected value of x is just mu x. Simplify this one more step, and I get that's a very important result. All right, this down here at the bottom of the page is a very important result. The variance can be found from knowledge of the first and second moments. The second central moment, which is the variance, which is the square of the standard deviation being the mean spread of values about the mean value. The variance can be found by knowledge of the mean squared value and the mean. If I know the first moment and the second moment, I can find the second central moment very easily. So commonly, we're just going to find the means and the mean squared values and move on. All right, let's use our properties to do another example. All right. Actually, this is a two-part example. I told you I was going to do three examples. I'm actually going to do one more example in two parts. So in this case, I'm going to let my function of my random variable be a x plus b, right? Excuse me. Yes, that's right. And this is going to be a new random variable y. So y, x and y are linearly related to one another. X and y are linearly related. And I'm going to assume I know the mean value and mean squared value of x, and what I want to find is the mean and mean squared value for y. And let's use our properties. The mean value of y, that's just the expected value of y. That's going to be the expected value of a x plus b. Using our properties, this is going to be the expected value of a x plus the expected value of b. B is a constant. So this is just going to be a times the expected value of x plus b. And this is a times mu x plus b. So in this case, if I know the mean value of x, I can find the mean value of y just through this simple relationship. And again, I apologize for sometimes making my mu's backwards. It's a bad habit. It's years old and it's hard for me to fix. I'll try to do better. I know that's annoying. My students have told me that over the years. Let's find the variance of y. All right, the variance of y is the expected value of y minus mu y quantity squared. All right, and this is going to be the expected value of ax plus b minus a mu x plus b quantity squared. All right. I'm substituting in the result from the first part of this example right there. All right. Square this out and simplify it a bit. Well, let's simplify a bit before we square. We're going to get a squared times x minus mu x squared. Apply properties of my expectation. I can pull the a out. I get a squared times the expected value of x minus mu x squared. And this, of course, equals a squared times the variance of x. And the variance of x is, one last step, I get a squared times the mean squared value minus the square of the mean. Okay? So if I have x and y that are linearly related to one another, and I know the mean and the mean squared value for x, I can find the mean and mean squared value for y. It's just that simple. All right? That is all I have for you for today. In the next video, we will look at the mean and mean squared values and standard deviations and variances of several common random variables. And that'll be all for this module. As usual, if you have any questions, please contact me at your earliest convenience, and I will answer any and all questions as fully as I am able. Have a nice day. Bye-bye.